Welcome to Web Handling. My name is Dave Roysum. I am very excited to continue a new mini-series on old topics. That is, conference papers that I gave some time ago. A long time ago. Why would you want something old? My first answer is that it is still timely today. In other words, the essentials have remained unchanged. My second is that some of you suffer from web machine vibration. This is one of the earliest and one of the very few publications on the subject. As machine speeds increased, so did the instances of speed-limiting vibration. However, this was not just true of the paper industry, where commercial speeds had just passed 3,000 meters per minute, or 10,000 feet per minute. It was and is still found at much lower speeds for winding certain compressible products, such as nonwovens and tissue. It is also seen on machines whose design is what we might term, in the best politeness I can muster, immature. While I had done static and dynamic finite element modeling a half-decade prior, the field work that followed made that work sing. Vibration analyzers were so expensive back then that the entire Beloit Corporation only owned one, and I had to borrow it from the Press Engineering Group. Thank you so much, John Creedeman. Well, let's buckle up and take our motion sickness pills. It's going to get a bit rough.
All winders vibrate during operation. The severity of vibration may be barely noticeable or a minor annoyance. However, in many instances, winder efficiency can be reduced because slower operating speeds may be required in order to avoid snap-offs and thrown rolls. Roll quality can be reduced by web breaks resulting from unstable unwinds or tension control, and by rough slitter cuts resulting from slitter vibration. Maintenance costs can be increased due to frequent repair of machine components, such as clutches, couplings, and bearings, resulting from increased dynamic loads. Finally, worker health and safety can be jeopardized if vibration results in physiological stress, noise, or the threat of thrown rolls. For these reasons and others, vibration can be a costly problem which deserves diagnostic and remedial action. Vibration causes include roll imbalance, which produces a once-per-revolution forcing function that can excite a structure to resonance, and roll-sidedness of paper rolls, which are neither concentric nor round. Small bumps or sides on unwind rolls cause web tension fluctuations, and sided rewind rolls cause wind-up station vibration. The unwind is the single largest contributor to web instabilities such as sheet flutter and snap-offs. Resulting problems also include rough slitter cuts, ragged roll edges, and the need to limit operating speeds. These web instabilities can be caused by unwind roll imbalance, as seen in this animated model. Rolls of paper have imbalances which are orders of magnitudes worse than steel rolls. These imbalances drive the unwind stand to vibrate, which is then transmitted into the sheet run as tension fluctuations. Reducing unwind vibration can be accomplished by winding well-structured reels onto spools which are balanced and have good journals. Additionally, the unwind system must be stiff, with the reel spools held securely in rugged stands and supported by a substantial foundation. However, as we will see in the next animation, stable unwind stands are necessary, but not sufficient to provide stable web runs. If the unwind log is out of round, the web surface speed is less at a small radius than when the unwinding tangent is at a larger radius. This causes strain changes and therefore tension fluctuations which will be transmitted into the sheet run even if the unwind stand is stable. To reduce log-sidedness, we must make concentric and round unwind logs at the reel by good structuring using tension, loading, and center wind parameters. To keep a log concentric from the time it is wound until it is ready for unwinding involves good reel handling practices. The log should not be set on the floor, bumped against other logs, or loaded roughly into the unwind stands. Also, if the logs are going to sit for a while, a Sunday drive should be considered to slowly rotate the log. Additional requirements for a stable sheet run include a well-tuned tension system and drive, as well as short draw lengths. The unwind is only one of many rolls in the winding system that can excite vibration, as seen in this graph of roll frequencies as a function of rewound diameter during the winding of a typical set. Winder speed during acceleration, run, and deceleration is seen on the bar graph at the right. All rolls are imbalanced to some degree, which produces a once per revolution sinusoidal forcing function that can excite resonance. The frequency of excitation is the rotational frequency of a roll, and sometimes integral multiples of the frequency if paper rolls are sighted or steel rolls misaligned and loosely mounted. The force produced by a roll is proportional to the weight of the roll, eccentricity, velocity squared, and inversely proportional to diameter squared. As seen from this graph, the rewound and unwind paper rolls can produce large driving frequencies up to 40 Hz, and the smaller diameter slitter rolls can generate forcing functions at frequencies up to 80 Hz for an 8,500 feet per minute winder. Additionally, roll beating between rolls rotating in dynamic vicinity of each other can generate sum and difference beat frequencies. If any of these rolls rotates at a frequency nearly equal to one of the many system resonances, vibration amplitudes can suddenly increase by almost an order of magnitude. Resonance is the severest condition of vibration. However, not all resonances create functional problems. In order for resonance to develop to unacceptable levels, the forcing function due to roll imbalance or sightedness must be of sufficient magnitude, act in the direction of the resonant mode, act near an antinode, and act for a sufficiently long time. As seen in this graph, excitation occurs at all frequencies up to and exceeding 40 Hz. This makes winder resonance inevitable. Therefore, good design is based on reducing the number and severity of resonances. Good machine dynamic performance begins with a foundation that is rock solid under all conditions of operation. If foundation vibration can be sensed without instruments, which is about 1/1000th of an inch peak to peak, the foundation is probably inadequate. In the foundation bending mode shown, we can see how the foundation bounces vertically in response to vertical excitation from the paper rolls if the winder is positioned over an unsupported section of flooring. This foundation may be adequate from conventional load capacity or stress-based design criteria. However, in order to achieve acceptable machine stability, winder foundation design must be based on dynamic considerations as well as static strength. This requires either very conservative design or the application of finite element modeling to determine foundation geometry. In the foundation twisting mode, we see that even a better and more typical foundation design, where the winder is supported directly underneath by columns, is still prone to vibrate. This mode is excited by machine direction forces which can easily overcome the bending stiffness of typical sill beam designed foundations used in paper mills. Twisting modes are easy to identify because the flooring vibrates more in areas that are some distance away from the winder. Fortunately, twisting modes can be reduced somewhat by placing jack posts under flooring that experiences large vibration. However, this approach will only go so far because the fundamental problem of inadequate foundation stiffness has still not been addressed. As seen in this and the following mode, convention column foundation design is often inadequate for winders. In the foundation shearing mode, horizontal forces cause horizontal motion of flooring and a machine. This can occur when the winder flooring is separated from the machine room flooring by expansion joints. Though expansion joints are necessary for thermal expansion, they have sometimes been misapplied in order to provide vibration isolation. A better solution is to reduce amplitudes of vibration by specifying extremely stiff foundations at the winder and locating labs and offices away from a winder. We cannot design foundations such that all resonances have a frequency greater than the exciting rules in a winder. We can only minimize the number and severity of resonances. A conservative design approach would be to specify 2 continuous walls underneath the winder base plates, spanning from the unwind to the front drum. The alternative, which can be more costly, is to commission finite element modeling to optimize design. In addition to foundation modes of vibration, the winder itself has numerous modes of resonance. The lowest frequency mode of winder vibration is the machine direction frame and rider roll mode, which occurs at about 13.6 Hz for a typical 300-inch wide 2-drum winder. This mode is driven by machine direction forces of the rewound roll and is coupled with the foundation twisting and shearing modes for a system resonance. It is important to view a winder as a system whose behavior is determined by the mass and stiffness distribution of the foundation and the winder. Though this mode is the lowest frequency mode, it cannot be easily excited and therefore is relatively benign. In order for strong vibration to develop, the driving force must be located near the antinode. In this mode, however, the driving force is the paper roll, but the antinode is at the rider roll beam. The next vibration mode is the first vertical. In this mode, the sighted rewound roll is driven vertically as it rotates on the drums. This motion also drives the rider roll vertically, much like an engine camshaft lifting a valve. This mode is one of the worst vibration problems and is especially severe for bulky paper grades such as kraft and book, as well as some lightweight coated grades. Vibration starts as an audible rumble at small rewound diameters during acceleration. The vertical motion of the rider roll may develop such that the rider roll lifts off the set and the paper rolls are thrown from the winder. Attempts to reduce the severity of this mode by increasing the rider roll stiffness by using direct acting cylinders can improve the situation somewhat. Attempts to reduce severity of this mode by various damping mechanisms, including friction and tuned dynamic dampers, have met with little success. A total solution to this problem mode remains undiscovered. The next vibration mode is the machine direction rider roll beam mode. In this mode, the rider roll beam bends horizontally in the machine direction as a simply supported beam. The wound rolls take a similar shape to the rider roll beam, except they are of a smaller magnitude. This mode, which is similar to mode 2, is also difficult to excite. The only way for the rewound roll to drive the rider roll assembly sideways is through tangential forces at the rider roll nip. These forces will tend to cause the rider roll to change speed cyclically as it rotates, but will not easily transfer horizontal forces to the beam because the roll is light and relatively easy to rotate. All modes, both benign such as this one and serious like the first vertical, will show up on natural frequency testing. Therefore, it is an important aspect of vibration studies to determine which mode is harmless and which interferes with winder operation. Animation of Mode 5, as well as others, will not be shown because they only involve peripheral components, such as barriers, cross ties, and ejector beams. These members can undergo large vibration without harm to the winder or disrupting the winding process. In Mode 6, all major components move in the machine direction. However, the rider roll assembly is 180 degrees out of phase with the rest of the winder, which includes the rewound roll and frames. This mode again is relatively benign, but for different reasons. This first of many complex mode shapes involving out-of-phase movement of components is extremely difficult to excite to large amplitude because strong forcing functions are rarely directed in two opposite directions at the same time. Additionally, this mode, which involves nearly all winder components, would require tremendous forces in order to move so much mass to significant velocities. In the cross-direction frame mode, the framework bends in the cross-machine direction as a cantilever beam, and the rider roll beam follows the frame motions. This mode is again difficult to excite to severe resonance because strong cross-direction forces are found only rarely. Imbalanced and sided rolls generate forces primarily in the machine and vertical directions. If one does encounter strong cross-direction movement, it can be an indication of either a bent journal or severe misalignment of a roll or coupling. Vibration analysis can also be used to specify maintenance on rotating elements such as bearings, rolls, couplings, belts, and chains. When diagnosing vibration problems, the vibration should be viewed as a symptom of more fundamental problems with the machine or operation. There are two rocking modes which have similar mode shapes and frequencies. These rocking modes are driven by a sided rewound roll which rocks from drum to drum as it rotates. The drums in turn bend up and down, but out of phase. These are very serious problem modes which usually develop at larger paper roll diameters and may be severe enough that the paper rolls leave one drum and are thrown from the winder. In practice, the safest approach is to reduce the speed of the winder until the rocking amplitudes are acceptable. Additionally, this mode can be improved by designing larger diameter drums which not only increase drum stiffness but also increase the containment angle defined by the centers of the paper roll and drum. In the machine direction frame scissors mode, the front and back framework bend out of phase with each other in the machine direction. The rewound rolls and rider roll follow the movement of the end frames. This is an example of the antisymmetric mode, where motion is equal in magnitude but opposite in direction on each side of the machine's center line plane of symmetry. Again, it is difficult to excite. In addition to these modes shown, there are an infinite number of higher modes which are of lesser concern. The higher modes require considerable power to contort the structure into complex shapes at high frequencies. Be aware, however, that these examples shown are for a typical two-drum winder. Each winder will have its own characteristic modes and frequencies which depend primarily on machine width, but also on other design parameters. It is the job of the vibration analyst to identify these modes for his particular winder. Now that we have covered some aspects of the causes, effects, and cures for winder vibration, we need to develop a problem-solving strategy. With so many rolls, excitation frequencies, and potential resonances, how do we go about analyzing and reducing winder vibration in a mill situation? First, we gather data from operator observations, surveys by touch, and vibration measurements to develop a clear picture of the problem. Next, we must define how vibration hinders the finishing room operation. A well-defined goal will enable a vibration specialist to more quickly determine how to meet our objectives. Modes of vibration can then be identified by striking the winder at various locations and in various directions, while measuring mode shapes and natural frequencies. During operation, vibration peaks at all frequencies can be monitored to identify which of the numerous modes vibrates unacceptably. Finally, the driving member needs to be identified. The frequency of a severe vibration will be an integral multiple of the rotational frequency of the offending roll. If there is more than one roll turning at a frequency, each can be run separately at resonance to identify the offender. If there is more than one mode of serious vibration, each should be diagnosed separately. Now that the vibration's character and the offending roll has been identified, we can attempt vibration reduction. Increasing the stiffness of any member that undergoes a large relative movement can increase natural frequencies and reduce vibration amplitudes. Strategically placed gussets from a vibrating member to a nearby stable member is often the most economical solution if feasible. Doubling the mass of a member that vibrates severely can cut amplitudes in half. However, natural frequencies will also be reduced. Another approach, though more difficult, is high tuning by reducing the mass while maintaining the stiffness of a vibrating member. Reducing excitation forces coming from steel rolls involves balancing to about 0.02 of an inch total indicated runout at top speed. Additionally, alignment of all rolls to about 0.005 of an inch will not only reduce axial forces, but improve the overall operation. Occasionally, certain problems lend themselves to damping if relative motions of a member are primarily in one direction and are large in magnitude. Also, isolating vibration by interrupting the path of transmission with a joint can protect sensitive equipment from harmful vibration. Though diagnosing winder vibration can be difficult, the advantages are a smoother and more efficient finishing room operation. Winder vibration can be reduced.
There had been very little winder vibration work prior to this, mainly by David Daly and later by Dr. Mark Franson, also both of Beloit Corporation. There also had been very little work since. Alex Olshansky, again from Beloit, described the characteristic property of bouncing materials better than anyone else. I extended that principle in a very obscure but very well done machine builder magazine that is still in current publication, the Tappi Journal. There, I showed how to tell whether the material or the machine was mostly responsible for the debilitating vibration. Thank you so very much for watching this module in my Plant Practical video series. Stay tuned for the next clip where we will describe something that nearly everyone cares about: wound roll quality. See you next time.